Welcome! In this session, we'll dive into problem number 2216, minimum deletions to make array beautiful. This is an interesting problem that challenges us to optimize an array based on specific constraints. We'll explore different approaches to solve it, evaluate their complexities, and derive the most efficient solution. Let's get started. In this problem, you are given a zero-indexed integer array called nums, and your goal is to make this array beautiful. An array is considered beautiful if, for every pair of indices I and j in the array, where I is even and j is the next consecutive index, the values at those indices are not equal. In other words, for any even index I, the value at nums, I, cannot be the same as the value at nums, I plus 1. To achieve this, you are allowed to perform deletions. Each time you delete an element, the rest of the array shifts to fill the gap, and the indices are reassigned accordingly. The task is to determine the minimum number of deletions required to make the array beautiful. The input is a list of integers representing the array, and the output is a single integer representing the minimum deletions needed. Let's look at an example to better understand the problem. Suppose the input array is 1, 2, 3, 4, 5. In this case, the array is already beautiful because it satisfies the condition that for every even index I, the value at nums, I, is not equal to the value at nums, I plus 1. For example, at indices 0 and 1, 1 equals 2, at indices 2 and 3, 3 equals 4. Since all the pairs meet the condition, no deletions are needed, and the output is 0. Now, consider a different example where the input array is 1, 1, 2, 3, 4. Here, the array is not beautiful because the pair at indices 0 and 1 violates the condition, as nums, 0, is equal to nums, 1. To fix this, we can delete one of the 1's at index 1. After this deletion, the array becomes 1, 2, 3, 4, which now satisfies the condition nums, 0 equals nums, 1, and nums, 2 equals nums, 3. Therefore, the minimum number of deletions required is 1. Let's examine another example where the input array is 1, 1, 1, 1, 1. This array requires more deletions to become beautiful. To ensure that adjacent elements at even and odd indices are distinct, we can delete 3 elements. For instance, deleting the elements at indices 1, 3, and 4 results in the array 1, 1, 1, which satisfies the condition. Thus, the minimum number of deletions required in this case is 3. Keep in mind that the goal is always to minimize the number of deletions while ensuring the array is beautiful. Finally, let's consider some constraints and edge cases. The array can have a length between 1 and 100,000, and each element can be as large as 100,000. For edge cases, if the array contains only a single element, it is automatically beautiful, and the output is 0. If all elements in the array are the same, like 5, 5, 5, 5, you will need to delete enough elements to ensure no two adjacent elements at even and odd indices are the same. Another interesting scenario is when the array alternates between two values, such as 1, 2, 1, 2. In such cases, the array might already be beautiful, requiring 0 deletions, depending on how the elements are positioned. These examples and constraints highlight the broad range of scenarios you may encounter while solving this problem. To solve this problem, we first considered a brute force approach. The intuition behind this method is straightforward. It ensures the array becomes beautiful by checking if every even-indexed element differs from its following odd-indexed element. If they are equal, one of them is removed, and the process is repeated until the condition is satisfied. However, there are important observations to note about this approach. Removing elements dynamically while iterating creates inefficiencies because every deletion causes subsequent indices to shift, which means the array must be re-evaluated. This results in nested iterations, leading to a time complexity of n squared. While the space complexity is low since no additional data structures are used, the trade-off is clear. This approach becomes impractical for larger arrays, especially when n can go up to 10 to the power of 5. It's simple to implement but computationally expensive for large inputs. A more efficient solution is the optimized approach, which uses a greedy two-pointer technique. Instead of repeatedly iterating and deleting elements, the idea here is to build the beautiful array incrementally. This is done by using 2 pointers, a write pointer, which keeps track of where the next valid element should be placed, and a read pointer, which traverses the original array. As we iterate, for every even index in the constructed array, we ensure the current element differs from the last written one. If they are equal, we skip the current element, effectively treating it as a deletion. This process continues until we've traversed the entire array. At the end, the difference between the original array size and the position of the right pointer gives us the total number of deletions. This approach avoids the inefficiencies of shifting elements dynamically and guarantees that the beauty condition is maintained at every step. The optimized approach offers significant improvements in efficiency. With a time complexity of O(n), we only traverse the array once, and the space complexity remains O(1), since no additional structures are required. This makes it highly scalable for large inputs. Compared to the brute force method, the greedy two-pointer technique is faster and avoids redundant computations. The key insight here is that we don't need to physically delete elements from the array. Instead, we simulate deletions by constructing a valid array incrementally, which ensures correctness without the overhead of shifting elements. By leveraging the structure of the problem, this strategy achieves optimal performance while remaining simple and intuitive. Altogether, the greedy approach is the best choice for this problem, offering a clean, efficient, and scalable solution to ensure the array meets the beauty condition with minimal deletions. To solve this problem, we want to determine the minimum number of deletions required to make an array beautiful. An array is considered beautiful if, for every pair of adjacent elements where one is at an even index and the other is at an odd index, their values are different. This means that for every valid even index I, the condition ARR I equals RR I plus 1 must hold. If two adjacent values in these even-odd index pairs are the same, the array is not beautiful, and we need to fix this by removing elements. To approach this, we start by initializing a counter called Deletions to track the number of deletions we perform. We also use a pointer I to iterate through the array step by step. With these in place, we can systematically check and modify the array to meet the condition. Now, we begin iterating through the array. Starting with the first even index, which is I equals 0, we check whether the condition ARR I equals RR I plus 1 is violated. If it is, meaning ARR I equals RR I plus 1, we increment the deletions counter and logically remove the element at the odd index I plus 1. This ensures the condition can be checked again for the next pair of elements. However, if the condition is satisfied, we simply move the pointer to the next even index by incrementing I by 2. For edge cases, such as when the array has a length of 1 or 0, no deletions are necessary since the array is already beautiful by default. Additionally, we make sure to stop the iteration before accessing any out-of-bound indices by checking that I plus 1 is within the length of the array. Finally, once all necessary deletions are performed, the total value of the deletions counter is returned as the result. There are a few key insights that make this algorithm both efficient and reliable. First, we only need to check the condition for even indices because the problem explicitly defines the adjacent relationships as being between even-odd index pairs. Second, the algorithm follows a greedy approach, meaning at each step, we make the smallest possible change by removing ARR I plus 1 when the condition is violated. This ensures we fix the issue locally without any unnecessary deletions. Additionally, the algorithm naturally handles edge cases such as arrays of size 1 or 0 by skipping the iteration entirely and returning 0 deletions. From a data structures perspective, we work directly with the input array and simulate deletions by skipping indices, avoiding the overhead of creating a new array. This results in a space-efficient solution. The time complexity is O(n), as we process each element at most once, and the space complexity is O(1), since no additional data structures are used. Let's walk through an example to see the algorithm in action. Given the input array ARR equals 4, 4, 3, 3, 2, we start with I equals 0. Comparing ARR 0 and ARR 1, we see that 4 equals 4, so the condition is violated. We increment the deletions counter to 1 and remove ARR 1, resulting in the array 4, 3, 3, 2. Now, comparing ARR 0 and ARR 1, 4 is not equal to 3, so the condition is satisfied, and we move to the next even index, I equals 2. Comparing ARR 2 and ARR 3, we find that 3 equals 3, so the condition is violated again. We increment the deletions counter to 2 and remove ARR 3, leaving the array 4, 3, 2. Finally, comparing ARR 2 and ARR 3, we see that 3 is not equal to 2, so the condition is satisfied. At this point, I equals 4, which is out of bounds, so we stop. The total number of deletions is 2, which is returned as the result. This solution implements the algorithm to solve the problem of finding the minimum deletions required to make an array beautiful. Here's a detailed explanation. 1. Initialization. We start by initializing deletions to 0. This will keep track of the number of elements we remove from the array. The length of the input array nums is stored in int for convenience. 2. Iterate through the array, using a for loop. We iterate through the array from index 0 to n2, inclusive. This ensures that we can compare each element with its next neighbor. 3. Check conditions for deletion. For each index I, we check 2 conditions. deletions, %2 equals 0. This ensures that the current index, after accounting for previous deletions, is even, as we only care about adjacent pairs where one element is at an even index and the other at an odd index. Nums, I, equals nums, I plus 1, this checks if the current element is equal to the next one, which violates the beautiful condition. If both conditions are met, it means we need to delete the current element to maintain the beautiful property, so we increment the deletions counter. For handle odd length, after the loop, if the remaining length of the array, i.e., n deletions, is odd, we need to delete one more element to make it even. This is because a beautiful array must have an even length to form valid adjacent pairs. We increment deletions if this condition is met. 5. Return the result. Finally, we return the total number of deletions required, stored in the deletions variable. This solution ensures that we traverse the array only once, making it efficient with a time complexity of O(n). The space complexity is O(1), as we use only a constant amount of additional memory. This is the Java implementation for LeetCode problem number 2216, minimum deletions to make array beautiful. The logic mirrors the provided Python implementation, iterating through the array to determine how many deletions are necessary to ensure the resulting array forms valid adjacent pairs. Key differences include Java's type declarations for arrays and variables, and the use of standard Java syntax for loops and conditionals. The solution is efficient and concise, directly addressing the problem requirements. To solve this problem, we start with the array nums equal to 1, 1, 2, 2, 3, 3. First, we initialize 2 variables. Deletions is set to 0 to track the number of elements we remove, and n is set to 6, the length of the array. In the first iteration, with index I equal to 0, we calculate that deletions modulo 2 equals 0. Since nums 0 equals nums 1, both are 1, we increment deletions to 1. Instead of explicitly removing nums 0, we use deletions to account for it being skipped. Moving to the second iteration with I equal to 1, this time, deletions modulo 2 is also 0, but nums 1 does not equal nums 2, 1 is not equal to 2, so we do not need a deletion here. In the third iteration, I is 2, and now, deletions modulo 2 equals 1, meaning this element naturally alternates, and no deletion is required. Next, in the fourth iteration with I equal to 3, deletions modulo 2 equals 0 again, and nums 3 equals nums 4, both are 2. Here, we increment deletions to 2. In the fifth iteration, I equals 4, and although deletions modulo 2 equals 0, nums 4 does not equal nums 5, 2 is not equal to 3, so no deletion is needed. Finally, we check if the remaining array length, n minus deletions, is even. Since it is, no additional deletion is required. The total deletions are 2. Now, let's look at an example where nums equals 1, 1, 1, 1, 1. We begin by initializing deletions to 0 and n to 5, the length of the array. In the first iteration, with I equal to 0, deletions modulo 2 equals 0, and nums 0 equals nums 1, both are 1. We increment deletions to 1. In the second iteration, I equals 1, and again, deletions modulo 2 equals 0, and nums 1 equals nums 2. This triggers another increment in deletions to 2. For the third iteration, I equals 2, and once more, deletions modulo 2 equals 0, and nums 2 equals nums 3. Deletions increases to 3. In the fourth iteration, I equals 3, and the pattern continues, I deletions, modulo 2 equals 0, and nums, 3, equals nums, 4. Deletions is increment to 4. After the loop, we check the remaining array length, n minus deletions. Here, it equals 1, which is odd, so we make one final deletion to balance it, resulting in deletions equaling 5. This ensures the array satisfies the alternating condition. Finally, consider the example where nums equals 1, 2, 3, 4. We start by initializing deletions to 0 and n to 4. In the first iteration, I equals 0, and I deletions, modulo 2 equals 0. However, nums, 0, does not equal nums, 1 is not equal to 2, so no deletion is needed. For the second iteration, I equals 1, and now, I deletions, modulo 2 equals 1, which means this element naturally alternates, so no deletion is required. In the third iteration, I equals 2, and I deletions, modulo 2 equals 0, but nums, 2, does not equal nums, 3 is not equal to 4. Again, no deletion is needed. After completing the loop, we check if the remaining array length, n minus deletions, is even. Since it is already even, no additional deletions are required. The result is that no elements need to be removed, and deletions remains at 0. To analyze the time complexity of this solution, we start by examining the main loop. The loop iterates through the array nums of length n, running from index 0 to n2. This means the total number of iterations is n1, which is linear in terms of the size of the input. Within each iteration, we evaluate two conditions: whether the current index, adjusted for the number of deletions, is even, and whether the current element equals the next element. Both of these checks are constant time operations, or O1. Similarly, incrementing the deletions counter when needed is also an O1 operation. After the loop, there is a single post-loop condition to ensure the final array length is even, which is another constant time operation. Since all the operations inside and outside the loop are constant time, the overall time complexity of the solution is determined by the loop itself, which is O(n). Now let's consider the space complexity of the solution. The algorithm only uses a few scalar variables, such as deletions, n, and the loop variable I. These variables occupy a fixed amount of memory, irrespective of the size of the input array. Importantly, no additional data structures are used, and the input array nums is neither modified nor duplicated. This ensures the space complexity remains constant, or O1. When analyzing different scenarios, the time complexity remains consistent. In the best case, where no deletions are needed because the array is already beautiful, the loop still runs through all n elements, resulting in O(n) time. In the average case, where some deletions are required, the number of iterations remains the same, so the time complexity is still O(n). Even in the worst case, where nearly every adjacent pair violates the condition, the loop does not run additional iterations, and the time complexity remains O(n). This consistency makes the algorithm highly efficient. When comparing this optimized approach to a more naive solution, the advantages become clear. A brute force method might involve repeatedly deleting elements until the array meets the conditions for being beautiful. However, each deletion in such an approach could require shifting elements in the array, leading to a time complexity of O(n) squared, in the worst case. In contrast, the optimized solution solves the problem by iterating through the array just once while using a counter to track deletions. This reduces the time complexity to O(n), which is a significant improvement. Additionally, the mathematical reasoning supports this efficiency. The loop runs 4n1 iterations, and each iteration involves constant time operations, making the total time complexity proportional to the size of the input, or O(n). Furthermore, since no additional memory structures are used, the space complexity remains O(1). In conclusion, this optimized solution is both time efficient and space efficient, addressing the problem in the most effective way possible. Let's start by addressing some common mistakes that can occur when solving this problem. First, misunderstanding indexing rules is a frequent error. Since arrays in programming typically use zero-based indexing, it's easy to confuse even and odd-indexed elements. This can lead to skipping valid comparisons or accessing the wrong indices, which can break your logic or even cause runtime errors. Another issue is failing to test edge cases. For example, arrays with only one or two elements, or arrays where all the elements are identical, can behave differently than you might expect. Without handling these properly, your solution might fail or produce incorrect results. Lastly, relying on an inefficient brute force approach is a common pitfall. While it might seem straightforward to use nested loops to compare every even-indexed element with every odd-indexed one, this leads to a time complexity of n squared. For large inputs, such as those with n up to 100,000, this approach becomes impractical and will likely time out during execution. Now, let's go into two more common mistakes. Off by one errors are another frequent issue. These occur when loops start or end at the wrong index, which can lead to incomplete checks or even out-of-bounds errors. This is especially problematic in edge cases where there's little room for error. Another mistake is overlooking constraints. It's critical to consider whether the input array adheres to all the given requirements and to handle cases where no solution is possible. For example, assuming the array is always valid or neglecting to account for edge scenarios can lead to unhandled exceptions or incorrect results. To avoid these pitfalls, always take a moment to carefully validate and plan your approach before diving into the implementation. In interview settings, recognizing patterns and problems like this one can give you an edge. Many array challenges involve alternating or pairing elements, so watch for patterns like even-odd indices or specific value comparisons. To optimize your solution, strive for an n time complexity by iterating through the array only once and directly applying the necessary checks. Clarifying questions are also key. Ask about constraints, edge cases, and whether inputs like empty arrays or arrays with all identical elements need special handling. When debugging, focus on index-based issues by printing intermediate indices and values during execution to catch off-by-one errors early. If your initial approach is brute force, it's fine to explain it first, but make sure to highlight its inefficiencies and then transition into presenting a more optimized solution. Finally, let's explore related problems and alternative approaches. Similar problems include LeetCode 922, 905, 75, and 280, which also deal with sorting arrays or arranging elements based on specific conditions. Understanding these problems can help you recognize recurring patterns. Now, for alternative approaches, the brute force method involves comparing every even-indexed element with every odd-indexed one. While simple to implement, its n squared time complexity makes it inefficient. A better option is the two-pointer technique, where you use one pointer for even indices and another for odd indices. This approach achieves n time complexity but requires careful pointer management. Another option is a sorting-based approach. By sorting the array and alternating elements between even and odd indices, you can achieve a valid arrangement. However, this may fail if specific pairings are required and comes with an n log n time complexity. Each method has its trade-offs, so choose the one that best fits the problem's constraints and requirements. Thanks for staying with us. We've summarized the key insights from problem number 2216 and explored practical takeaways to apply in similar scenarios. Don't forget to keep practicing and refining your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!